Okay, 1.3 exponents. Again, most of this stuff here is review of things we've done in the past. This is just going to help us review some of those materials or concepts that maybe just need brushing up in our minds. So a couple of goals. We're going to be simplifying expressions that have radicals, and then we're going to be simplifying and converting between exponent notation and radical notation. Some things we've done before, simplifying fractions, simplifying exponents. We've done this converting back and forth, but let's review it just briefly. I did email you the PDF of my notes, so if you want, you can use that instead of this to copy down, so then you don't have to look at copy all this down. But if you want to, here it is. You can pause and we'll move forward. So the big ones here that I like to remember when I'm looking at this, I'm going to zoom in a little. Here we go. The big ones are the adding the exponents when multiplying, subtracting the exponents when dividing, multiplying the exponents when taking a power of the exponents, and then like that distribution of the term to, distribution of the exponent to each of the terms inside of a parentheses, so long as we're talking about a monomial, not a polynomial. Be careful that you don't try to do that on a polynomial. Okay. Anything to the 0 is 1. We should remember that. And then a raised to the negative n is going to be 1 over a to the n. You also sometimes see that as 1 over a to the negative n is a to the positive n. So a long time ago I used to tell you guys a story about not living where you want to live and being unhappy with your living situation. So you move from the downstairs to the upstairs and you change your attitude. But hopefully it's been working with these long enough now that you feel pretty comfortable with how to manipulate exponents. So what we're going to do is we're just going to run through maybe some more complex examples than we've seen in a while or possibly ever seen and see how that goes. Okay. So got kind of start with an easy one here. We have m to the second, n to the negative third, n to the 1/2, m to the 2/3, and that's all raised to the 6th power. So of course there's lots of ways to go about doing these. The order in which you process this is not super important, so long as you're being careful. But we could rearrange moving our negatives where they need to go and our positives where they need to go. We can multiply through this exponent to each of the terms. We could subtract our exponents because we have some in the numerator and the denominator, so there's lots of steps to do here. What I would do when I see this is that I have a 1/2 and a 2/3 on my exponents, and 2 and 3 are both multiples of 6. So when I take the time to multiply the 6 by those exponents in the denominator, I won't have fractions anymore that I'm dealing with. So that'll make this problem much easier. So when I do that, I would consider that my first step. So I'm going to multiply that 6 through to every single exponent. Okay, don't miss any because then you won't be doing that one right. So m to the 12th, n to the negative 18th, 6 times 1/2, n to the 3rd, 6 2/3 is going to be m to the 4th. Well, now I don't have to deal with fractions, so hooray for that. Now at this point, I'm going to pull this guy down because he's negative 18 and add my exponents when he comes down here as a positive 18. So this is going to become negative 18 comes down, becomes positive 18 as our exponent. We already have a positive 3 on our end, so add them up, 21. So n to the 21st. Okay. Then I have an m to the 12th and an m to the 4th, and I just like to identify which term is larger, subtract the smaller from the larger, and then leave the term where the answer is positive. So in this case, 12 is larger than 4, so I'm going to subtract the 4 away and be left with m to the 8th. Well, where does the m to the 8th go? Think about it this way. If I were to write this all the way out and cancel terms, we would only have terms left in the numerator. So we must be leaving our m to the 8th in the numerator. Okay. Here's one where we're going to simplify radicals, reviewing simplifying radicals. So this is a 4th root, which means we need to have groups of 4 to move out of the radical as simplified. Turns out that 81 is 3 times 3 is 9, times 3 is 27, times 3 is 81. So 81 can be written as 3 to the 4th, a to the 8th, b to the 12th. So how many 3's do I have here? I have 3 times 3 times 3 times 3. There's one group of 4 3's multiplying together, so it gets to move out of the party. Cool. I'm going to leave my radical here to see if there's anything left behind. So the 3 gets to move out. And then I have a to the 8th. I can expand it all the way out if I need to. A, and I would have one group, two groups of 4. So I would have a times a coming out, which is a squared. No a's left behind. I dealt with all of those, dealt with all of the 3's. B to the 12th, well, I can write it all the way out, or I can say, well, how many groups of 4 are there in 12? Well, it happens to work out cleanly that there are 3 groups of 4 in B to the 12th, so I would have B to the 3rd, and the only thing left inside is just, this is always, anything is always times 1, so we can leave them in there. So do I need to write times the square root of 1? No, that's just excessive, so we simplify this out without the 1, saying 3a squared b cubed. Exciting. If there had been anything left in here, like if this had been a b to the 13th, I could have said I have one b left over, then I could have put that, and then I would have had to leave my radical, but in this case there's nothing remaining, so I don't have to write anything. This one's kind of a combination of both ideas where we're going to do some simplifying and see where we go from this. We're going to simplify this. I'm going to rewrite this as the quantity a plus b to the half over the quantity a plus b. Well, of course there's always an invisible or implied 1 here. So if I'm going to use my rules, I can say this is really just a number, and here's that same number, and they're raised to different powers. So same base, different power, so I can subtract the powers. Which one's bigger, 1 or 1/2? Well, we should be pretty comfortable with saying that 1 is bigger than a half. So I subtract 1/2 from 1, and I'm going to be left with a plus b to the 1/2. Well, then I ask myself, where does it belong, in the numerator or the denominator? Well, 1 is bigger, so this must be all that's left. Common mistake, people just say that's the answer. No. If I put that, it would have been living in the numerator. So we have to remember, it's not that there's nothing left in the denominator, but that everything's simplified to become a 1. So watch out for that. Because this is given in radical notation over here, probably be good habit to write this as 1 over the square root of a plus b. Well, you might say to yourself, there's a radical in the denominator here. Yeah, we know that. What they're asking us to do here is to convert between this form and this form. It's kind of a different way of doing it. So if you were to rationalize the denominator on this problem, you would be up here with your rationalized answer. And one last one. This one is kind of a doozy. We've got so many things going on here. X squared plus 2 to the 3 halves minus 2 times the quantity x squared plus 2. Okay, well, that seems a little tricky, but here is what we're going to do. Okay. Oh, I have this written down wrong. Let me fix that. I'm missing a parentheses. There we go. That's easier. Okay, so I have an x squared plus 2 and an x squared plus 2. Remember, things in the parentheses, a binomial can sometimes be treated as if it's one number, which can make things a little bit easier for us. So we in fact have something like, if I was going to write this in a simple way, I might say that this is sort of like a to the 3 halves minus 2a to the 1 half. If you notice, I have a 1 half here, and 3 halves is really, this is really a to the first times a to the 1 half. So I have a common term here. Over here it looks a little funny because we have a quantity represented as our a. And so we're going to pull out that a to the 1 half as a common factor. So x squared plus 2, our quote-unquote a, raised to the 1 half. Well, what am I left with when I do that? It's still all over x squared. Here, I'm left with, multiplied by the quantity, x squared plus 2, and that's all to the first, minus, well, what is this factored out going to leave us with? Simply a 1. All right, oops, squared. So when I have x squared plus 2 to the first, is that something I need to write? Do I need the first? No, I can just say that I have one of those quantities. So this is going to simplify to x squared plus 2 minus 2. Oh, well, that's kind of convenient that that would happen. It's like they wrote that problem that way or something. Yes, that's exactly what the textbook's doing. They're looking for you to use these tricks to show that you know how to do them. So this is going to become the quantity x squared plus 2 all to the 1 half still, plus 1 half minus 1 half goes to 0, and this is just x squared all over x squared. Oh, how convenient. X squared reduces with x squared because it's a form of 1, and we're simply left with x squared plus 2, quantity raised to the 1 half, and if you wanted to, you could write that in radical form as the quantity x squared plus 2, and that's all square rooted or under the radical.